Let us continue the miscellaneous exercise on chapter 5. Question number 16. If cos y is equal to x cos a plus y with cos a not equal to plus or minus 1, prove that dy by dx is equal to cos square a plus y upon sin a. We have two methods to do this question. We can directly differentiate and get the answer, but the answer will have x. We have to eliminate x by substituting for x. Look at the answer. The answer is in terms of y. We may make it an explicit equation by writing x equal to cos y upon cos of a plus y. If we differentiate this equation with respect to y, the answer will be in terms of y. Here we are going to differentiate with respect to y. We will get dx upon dy. X has been differentiated with respect to y here. We will use quotient rule, u and v. U dash, derivative of cos is minus sin y into derivative of y with respect to y will become 1 into v, which is cos of a plus y, minus u is cos y into v dash. Differentiation of cos is minus, so minus of minus plus sine of a plus y into derivative of a plus y is 0 plus 1 because y is differentiated with respect to y in this case, divided by v square term, which is cos square a plus y. The numerator is of the form sin a cos b minus cos a sin b, which is sin of a minus b. So, using this formula in the numerator, we get sin of a term is a plus y and b is y. So, a plus y minus y divided by cos square a plus y, and we get sin a divided by cos square a plus y, and this is the answer of dx upon dy, but we need to write dy upon dx. Therefore, we will write the reciprocals. Dy by dx is equal to cos square a plus y upon sin a. Since sin a is in the denominator, that condition cos a not equal to plus or minus 1 is given. If it is equal to plus or minus 1, a will be either 0 or pi, etc. So, in that case sin a will be 0. Division by 0 is not defined. Question 17. If x is a times cos t plus t sin t and y is a times sin t minus t cos t, find d square y upon dx square. This is an important question. For parametric equations, we have to find the second derivative. We have done the first derivative questions. This is second derivative. Let us first find dx by dt. A is a constant. A times derivative of cos t is minus sin t plus here product rule u and v, u dash into v plus u v dash, which is a t cos t. Now, we will find dy by dt. A times derivative of sin t is cos t minus of, we will use product rule, derivative of t is 1 into cos t plus t times derivative of cos is minus sin t. Plus cos t and minus cos t are getting cancelled, and we get minus of minus will become plus a t sin t. Let us find the first derivative dy upon dx, which is dy by dt upon dx by dt. We have to write dy by dt in the numerator. at sin t upon at cos t. Sin t over cos t is tan t. dy by dx is tan t. Now to find the second derivative, we are going to differentiate both sides with respect to x, because we need to get d square y upon dx square. So the left hand side becomes d square y by dx square. Here the right hand side term is in terms of t. We don't have a function of x there. So we have to use chain rule. We will differentiate tan function first, which is secant square t, and then t has to be differentiated with respect to x. Differentiation is done with respect to x here. Secant square t times dt over dx. We have the answer for dx by dt, which is at cos t. So dt over dx will be reciprocal of that, 1 upon at cos t. 1 by cos t is secant t, therefore we get secant cube t upon at. And this is an important question. This is the only question in the textbook, finding the second derivative of parametric equations. So you need to practice extra questions, finding the second derivative of parametric equations. Question 18. If f of x is equal to absolute value of x the whole cube, show that f double dashed of x exists for all real x and find it. We know the definition of the absolute value function. It is x for x greater than or equal to 0 and minus x for x less than 0. So using this definition, absolute value of x is x and cube will be x cube when x is greater than or equal to 0, and minus x the whole cube when x is less than 0, which is minus x cube. For all real values x greater than 0, f of x is x cube from the first definition, which is a polynomial. We know that polynomials are continuous and differentiable everywhere. Therefore, f of x is differentiable in this interval. That means f dashed of x exists for all real values greater than 0. Similarly, for x less than 0, that is for all real values less than 0, we know that the function is minus x cube. This is also a polynomial. Therefore, f of x is differentiable in this interval also. Now we will check the differentiability at 0. For less than 0 we have one definition, for greater than 0 we have another definition. So we have to check the differentiability at 0. Let us find LHD, left hand derivative. The formula is limit extending to 0 minus f of x minus f of 0 divided by x minus 0. Limit extending to 0 minus, that is approaching 0 from the left side of 0. So the definition is less than 0 definition we will be using. F of x is minus x cube and f of 0 is 0 upon x minus 0 is x, which is limit extending to 0 minus minus x square. By substituting the limit value we get 0. Similarly, let us find RHD, right hand derivative at x is equal to 0. Limit extending to 0 plus of f of x minus f of 0 upon x minus 0. Limit extending to 0 plus, we have to use greater than 0 definition, which is x cube minus f of 0 is 0 divided by x minus 0 is x. Limit extending to 0 plus x cube over x is x square, which is a polynomial. Directly we can apply the limit value, the answer is 0. LHD and RHD are same. Therefore, f of x is differentiable at x equal to 0. and f dashed of x will be, let us differentiate and write, for x greater than or equal to 0, f of x is x cube. Derivative of x cube is 3x square. And for x less than 0, the definition is minus x cube. Therefore, the derivative is minus 3x square. Now, we will check the second derivative. So, for all real values greater than 0, f dashed of x is 3x square, which is a polynomial. Therefore, f dashed is differentiable in this interval. Similarly, for all real values less than 0, f dashed of x is minus 3x square, which is again a polynomial. Therefore, f dashed of x is differentiable in this interval as well. Now, we will check the differentiability of f dashed of x at 0, because for greater than 0 one definition is there, for less than 0 another definition is there for f dashed. So, we need to check. At x is equal to 0, we are checking the differentiability of f dashed. LHD of f dashed is equal to limit x tending to 0 minus f dashed of x minus f dashed of 0 upon x minus 0 equal to limit x tending to 0 minus f dashed of x. For 0 minus we use less than 0 definition, which is minus 3x square minus f dashed of 0. So, x equal to 0 definition is here. By substituting x equal to 0, we get the answer 0. Divided by x minus 0 is x, which is limit x tending to 0 minus 3x square divided by x. By substituting the limit value 0, we get the answer 0. RHD of f dashed, limit x tending to 0 plus f dashed of x minus f dashed of 0 divided by x minus 0, which is limit x tending to 0 plus. For 0 plus, we use greater than 0 definition, which is 3x square, minus using the same definition x equal to 0, f dashed of 0 is 0 divided by x minus 0 is x, limit x tending to 0 plus 3x square divided by x, which is 3x. By applying the limit value, we get 3 times 0, which is 0. LHD of f dashed is equal to RHD of f dashed. Therefore, f dashed of x is differentiable at x equal to 0. And now we will write the answer for f double dashed. Therefore, f double dashed of x is, f dashed of x definition is 3x square for x greater than or equal to 0 and minus 3x square for x less than 0, from which we can write f double dashed. For x greater than or equal to 0, it becomes 6x, and for x less than 0, it becomes minus 6x. Therefore, f double dashed of x exists for every real value. Question 19. Using mathematical induction, prove that d by dx of x raised to n is equal to n x raised to n minus 1 for all positive integers n. We have to use mathematical induction method. We will take the given statement as p of n. Let us first prove that p of 1 is true, which is d by dx of x raised to 1, which is x, equal to n is 1, 1 into x raised to 1 minus 1, which is 0. We know that derivative of x is 1, so this is true. Let us assume that p of k is true, and we will write p of k statement, which is d by dx of x raised to k is equal to k times x raised to k minus 1. Now, we are going to prove that p of k plus 1 is true. P of k plus 1 statement is d by dx of x raised to k plus 1 is equal to k plus 1 times x power k plus 1 minus 1, which becomes k. Let us take the left hand side of p of k plus 1 statement, which is d by dx of x raised to k plus 1, and this can be split and written as x raised to k times x. To differentiate this, we will use product rule, which will be d by dx of x raised to k times x plus x raised to k times d by dx of x. And this result we can substitute from p of k, which is k times x raised to k minus 1 into x plus x power k times dx by dx is 1. This is k times x power, we will add the exponents, k minus 1 plus 1 will become k plus x raised to k. X raised to k is common and we get k plus 1, which is the right hand side. Therefore, p of k plus 1 is true whenever p of k is true. Therefore, p of n is true for all positive integers n. Therefore, the given statement is true, that is d by dx of x raised to n is n times x raised to n minus 1 for all positive integers n. 20th question. Using the fact that sine of a plus b is equal to sine a cos b plus cos a sine b, and the differentiation, obtain the sum formula for cosines. We have to get the formula for cos of a plus b, which is cos a cos b minus sine a sine b. Let us differentiate this equation with respect to x, that is, we are taking a and b both as functions of x, or we may differentiate with respect to a or with respect to b also. Let us do with respect to x. So, differentiation of sine is cos of a plus b, and then a plus b should be differentiated with respect to x, which is dA divided by dx plus dB divided by dx equal to, here we will apply product rule, derivative of sine a is cos a into derivative of a with respect to x is dA by dx into cos b plus sine a times derivative of cos b is minus sine b into derivative of b with respect to x, plus similarly we will differentiate the second term using product rule, derivative of cos a is minus sine a into derivative of a with respect to x, don't forget to write this dA by dx into sine b plus cos a times derivative of sine b is cos b into derivative of b with respect to x. In the first and the last terms, cos a cos b is common. Cos a into cos b times, we get dA by dx from the first term plus dB by dx from the last term. From the second and the third terms, we have minus sine a sine b common. So, minus sine a into sine b times, we get dA by dx plus dB by dx. And on the left hand side, we have cos of a plus b times dA by dx plus dB by dx. Cancelling dA by dx plus dB by dx throughout, we get cos of a plus b is equal to cos a cos b minus sine a sine b, and this is the result which we have to prove. Question 21. Does there exist a function which is continuous everywhere but not differentiable at exactly 2 points? Justify your answer. Let us consider f of x as absolute value of x plus absolute value of x minus 1. The graph of absolute value function x is this. We know that it is a continuous graph, there is no break in the graph, but it is not differentiable at x equal to 0, because as we approach 0 from the left side of 0, the derivative approaches minus 1. But as we approach 0 from the right side of 0, the derivative approaches plus 1. Otherwise also we know that if there is a sharp turning point in the graph, it won't be differentiable at that point. So absolute value of x is not differentiable at x equal to 0, but it is a continuous function. And the graph of absolute value of x minus 1 is this. It is a continuous function, but it is not differentiable at x equal to 1. Because of the same reason, as we approach 1 from the right side of 1 or left side of 1, the derivatives don't approach to the same value. The domain for this function is minus infinity to plus infinity. We will split the interval at 0 and 1. We know that absolute value of x is x for x greater than or equal to 0 and minus x for x less than 0. Similarly, the definition of absolute value of x minus 1 is x minus 1 for x greater than or equal to 1 and minus of x minus 1, which is 1 minus x for x less than 1. In the interval minus infinity to 0, that is less than 0 definition, we have to use absolute value of x becomes minus x, and for the interval 0 to infinity, the function is x. So in both these intervals it is x. Now let us write for absolute value of x minus 1. In the interval x less than 1 is these two intervals. So for x less than 1, the definition is 1 minus x. For x greater than or equal to 1, that is 1 to infinity, in this interval the function is x minus 1. Now let us add these definitions for each of these intervals, because the function f of x is absolute value of x plus absolute value of x minus 1. So we will add these two functions. Minus x plus 1 minus x becomes 1 minus 2x. In the next interval, it is x plus 1 minus x. It becomes a constant function 1. And in the third interval, it is x plus x minus 1, which is 2x minus 1. We will write f of x for each of these intervals. It becomes 1 minus 2x in the first interval, that is x less than 0, and it becomes a constant function 1 for 0 less than or equal to x less than 1, and it is 2x minus 1 for x greater than or equal to 1. For x less than 0, it is a polynomial. For x greater than or equal to 1 also it is a polynomial, and in this interval it is a constant function. We know that polynomial functions and constant function are continuous and differentiable everywhere. But we have to check the continuity and differentiability at 0 and at 1, as we have different definitions. Let us see the graph of this function f of x. For x equal to 0, the answer is 1. For x less than 0, it is a polynomial 1 minus 2x, which is a straight line. This is y equal to 1 minus 2x. And in the interval 0 to 1, it becomes a constant function 1. And then for x greater than or equal to 1, it is 2x minus 1. Y is equal to 2x minus 1, and this is y equal to 1. Look at the graph. It is a continuous function. There is no break in the graph, but it is not differentiable at 0 and at 1 because we have sharp turning points. You need not draw the graph for this question. I just explained with the graph so that it will be easier for you to understand. Now we will check the continuity and differentiability at 0 and at 1. LHL is equal to limit extending to 0 minus f of x. Limit extending to 0 minus. For 0 minus, we use less than 0 definition, which is 1 minus 2x. By substituting the limit value, we get 1. RHL is limit extending to 0 plus f of x. For 0 plus, we will use greater than or equal to 0 definition, which is 1. It is a constant. The answer is 1. F of 0 is, from the definition, x equal to 0 definition is 1. LHL equal to RHL equal to f of 0. Therefore, f of x is continuous at x equal to 0. Now we will check the differentiability. I will write f of x function here. It will be easy for me to copy the functions. 1 minus 2x for x less than 0, 1 for 0 less than or equal to x less than 1, 2x minus 1 for x greater than or equal to 1. Now LHD is limit extending to 0 minus. For differentiability, formula is f of x minus f of 0 divided by x minus 0. Limit extending to 0 minus, we use less than 0 definition, which is 1 minus 2x for f of x, minus f of 0. When x is 0, f of 0 is 1 divided by x. Limit extending to 0 minus, minus 2x over x becomes minus 2. The answer is minus 2. RHD is limit extending to 0 plus f of x minus f of 0 divided by x minus 0. Limit extending to 0 plus. For 0 plus, we have to use greater than 0 definition, which is 1, minus f of 0. F of 0 is also 1 divided by x. Limit extending to 0 plus 0 divided by any number becomes 0. The answer is 0. LHD is not equal to RHD. Therefore, f of x is not differentiable at x equal to 0. Now we will check the continuity at x equal to 1. LHL is equal to limit extending to 1 minus f of x. Limit extending to 1 minus. For 1 minus, we use less than 1 definition, which is the constant function 1. The answer is 1. RHL is equal to limit extending to 1 plus f of x. For 1 plus, we use greater than 1 definition, which is 2x minus 1. By substituting x as 1, we get 2 minus 1, 1. And f of 1 value is the same definition, 2x minus 1. 2 minus 1 is 1. All three are equal. LHL equal to RHL equal to f of 1. Therefore, f of x is continuous at x equal to 1. Now we will check the differentiability at x equal to 1. LHD is equal to limit extending to 1 minus. LHD formula is f of x minus f of 1 divided by x minus 1 equal to limit extending to 1 minus. For 1 minus, we use less than 1 definition, which is the constant function 1, minus f of 1. For f of 1, we use equal to 1 definition, which is 2x minus 1. So, f of 1 will be 2 minus 1, 1 divided by x minus 1. Limit extending to 1 minus 0 divided by x minus 1 becomes 0. Now, let us find RHD. Limit extending to 1 plus f of x minus f of 1 divided by x minus 1. Limit extending to 1 plus greater than 1 definition, which is 2x minus 1 minus f of 1 is 1 divided by x minus 1. Limit extending to 1 plus 2x minus 2 divided by x minus 1. Here 2 is common. The answer is 2. LHD is not equal to RHD. Therefore, f of x is not differentiable at x equal to 1. Therefore, the function f of x is continuous everywhere but not differentiable at x equal to 0 and at x equal to 1. Second question, if y is equal to, it's a 3 by 3 determinant, f of x, g of x, h of x, L, M, N, A, B, C. Prove that dy by dx is equal to f dashed of x, g dashed of x, h dashed of x, L, M, N, A, B, C. Note, to differentiate a determinant of any order, we differentiate one row or one column at a time, keeping other rows or columns unchanged. It's like product rule. So let us differentiate the given determinant. Dy by dx is equal to, we will differentiate the first row. Differential of f of x is f dashed of x into differential of x is 1. Differential of g of x is g dashed of x into differential of x is 1. And differential of h of x is h dashed of x into differential of x is 1. Keeping the other two rows same. Plus, now we will differentiate the middle row, keeping first and the third rows same. So we have to write the first and the third rows of the original determinant. F of x, g of x, h of x, third row is a, b, c. In the middle row, all three elements are constants. Derivatives are zeros. Plus, now we will keep the first and the second rows same. So we will copy the first and the second rows from the original determinant. Now differential of the third row, a, b, c are constants, we get 0, 0, 0. And we know that in a determinant, if one full row is 0, the determinant value becomes 0. Therefore, the answer is f dashed of x, g dashed of x, h dashed of x. Second row is LMN, third row is ABC. And the other two determinants are zeros. Question 23. This is an important question. If y is e raised to a cos inverse of x, where minus 1 less than or equal to x less than or equal to 1, show that 1 minus x square times d square y by dx square minus x dy by dx minus a square y equal to 0. Here in the function cos inverse of x is there, and we know that domain of cos inverse function is minus 1 to 1. That's why that condition is given. The given equation is y is equal to e raised to a cos inverse of x. Let us differentiate both sides with respect to x. We get dy by dx equal to, we have to differentiate e function first and then the power. Derivative of e function is the same, into derivative of the power a times, and derivative of cos inverse is minus 1 upon root of 1 minus x square. And remember, in proving the second order differential equation questions, if you get a denominator, take it to the other side and do the second derivative. That will be easier to do. That is, multiplying both sides by root of 1 minus x square, we get root of 1 minus x square times dy by dx equal to minus a times, this term can be substituted as y because that is the given equation. e raised to a cos inverse of x is y. So it will be easier to differentiate. Now we can differentiate this equation both sides with respect to x, or to make it easier, we can remove this square root by squaring both sides. So differentiation becomes easier to do. We get 1 minus x square dy by dx the whole square equal to minus will become plus a square y square. Now we will differentiate with respect to x. We will apply product rule to the left hand side. U dash derivative of u term is minus 2x into dy by dx the whole square plus u term is 1 minus x square v dash. To differentiate v term, power has to be differentiated first. Then the base dy by dx has to be differentiated, which is d square y upon dx square equal to a square is a constant, a square times. To differentiate y square, power has to be differentiated first, then the base has to be differentiated. Differential of the power is 2y into differential of the base y with respect to x is dy by dx. Now we can cancel 2 and dy by dx throughout. Now let us write the second term first. 1 minus x square times d square y upon dx square. Now we will write the first term minus x times dy by dx, and let us take this right hand side term to the left hand side, minus a square y equal to 0. Example 44, we will do the third subdivision. First two subdivisions are easy, you can try by yourself. See the third part. Y is log of log x to the base 7. Here the base is e. If the base is not mentioned, that means it is to the base e. We know the differentiation formula only for log x to the base e, which is 1 by x. So let us change the base. Change of base formula is log p to the base a becomes log p to the base e upon log a to the base e. So using this change of base formula, we will change this base 7. Log of log x to the base e divided by log 7 to the base e, which can be written as log of log x divided by log 7. Now we will differentiate both sides. Dy upon dx is equal to 1 upon log 7 is a constant. We will keep the constant and differentiate the numerator using chain rule. This log has to be differentiated first, then this log x. Differential of the first log function is 1 upon log x, and differential of the second log function is 1 upon x. The answer is 1 upon x log 7 into log x. Example 45. We have inverse trigonometric functions. First subdivision, y is cos inverse of sin x. Remember, if you have inverse trigonometric function outside, first simplify the function and then differentiate the function. Here we have cos inverse outside and sine function inside. Either you change sine to cos function or cos inverse to sine inverse function. So cos inverse can be changed to sine inverse using pi by 2 minus sine inverse of sin x formula, because we know that sine inverse of x plus cos inverse of x is pi by 2. Now this can be simplified. It becomes x. Now let us differentiate both sides with respect to x. The answer is minus 1. Pi by 2 is a constant, differentiation is 0. Second subdivision, y is tan inverse of sin x upon 1 plus cos x. Here also we have inverse trigonometric function outside and big expression we have. Let us simplify this expression. tan inverse of 1 plus cos x is 2 cos square x by 2. So we will write the numerator also as 2 sin x by 2 cos x by 2. We can cancel cos x by 2 and 2. It becomes tan inverse of sin x by 2 divided by cos x by 2 is tan x by 2. Now we can cancel tan inverse and tan functions. We get x by 2. Here also condition is not given, so directly we can cancel these two functions. Now let us differentiate both sides with respect to x. We get dy by dx equal to half into derivative of x with respect to x is 1. The answer is half. The third subdivision, y is sine inverse of 2 raised to x plus 1 divided by 1 plus 4 raised to x. This is an important question. Here also we need to simplify because we have inverse trigonometric function and a big expression within brackets. We have a formula sine inverse of 2x upon 1 plus x square is equal to 2 tan inverse of x. Let us write this given function in this form. Sine inverse of, I can split this power as 2 power x into 2 divided by 1 plus 4 raised to x can be written as 2 square whole power x, which is 2 power 2x, and I can write this as 2 raised to x the whole square. It's the same, x into 2 is also 2x. So I will write it as 2 raised to x the whole square. Now this function is in this form where x is 2 raised to x. So using that formula, this becomes 2 tan inverse of x in this function is 2 raised to x. We have simplified the function. Now we will differentiate. Differentiating both sides with respect to x, we get dy by dx equal to 2 is a constant. To differentiate tan inverse of 2 raised to x, we have to apply chain rule. Tan inverse has to be differentiated first, then 2 raised to x has to be differentiated. Differential of tan inverse of x is 1 upon 1 plus 2 raised to x the whole square into differential of a power x is a power x into log a. So using that formula, it becomes 2 power x into log 2. And into differential of the power x is 1 equal to, these two are like terms. 2 times 2 raised to x can be written as 2 raised to x plus 1 times log 2 divided by 1 plus 2 raised to x the whole square becomes 2 square raised to x, which is 4 raised to x. This is the answer. Example 47. For a positive constant a, find dy by dx where y is a raised to t plus 1 by t and x is equal to t plus 1 by t raised to a. These are parametric equations. We will first find dy upon dt. We will differentiate the exponential function and then we will differentiate the power. Differential of the exponentiation function a power x is a power x times log a. So using this formula, we get a raised to t plus 1 by t times log a. And then power has to be differentiated. Derivative of t with respect to t is 1 and derivative of 1 by t. The differentiation is minus 1 t power minus 2, which is minus 1 by t square. Now let us find dx by dt. Here base is a variable, power is a constant. We will use d by dx of x raised to n formula, which is n x raised to n minus 1. So by applying chain rule here, power has to be differentiated first, then the base. Differentiation of the power is a into t plus 1 by t whole power a minus 1. Now base has to be differentiated. Differential of t is 1 and differential of 1 by t is minus 1 by t square. We have to find dy by dx, which is dy by dt upon dx by dt. Be careful, divide it correctly. Dy by dt should be written in the numerator. Divided by dx by dt. These two terms are getting cancelled. Therefore, the answer is a raised to t plus 1 by t times log a divided by a times t plus 1 by t whole raised to a minus 1. Example 48. This is an important question. Differentiate sine square x with respect to e raised to cos x. So far, we have differentiated y with respect to one variable x, or with respect to t, with respect to theta. So, we have been doing differentiation with respect to a single variable. Whereas, in this question, we have to differentiate one function with respect to another function. It is not with respect to some variable here. If you have to differentiate one function with respect to another function, take the first one as u, the second one as v. We will find du by dx and dv by dx, and by division we can find du by dv. That is differential of the first function with respect to the given second function. Okay, let us calculate du by dx. Here we have to apply chain rule. Power has to be differentiated first, then the base sin x has to be differentiated. 2 sin x is the derivative of the power, and derivative of the base sin x is cos x. Now let us differentiate v function. Dv by dx is equal to, here e function has to be differentiated first, then the power cos x has to be differentiated. Derivative of e function is the same, into derivative of the power cos x is minus sin x. Now we have to find the derivative of the first function with respect to the second function, that is du by dv, which is du upon dx divided by dv upon dx. 2 sin x cos x divided by minus sin x times e raised to cos x. When you do division, be careful, du by dx is in the numerator here. The answer is minus 2 cos x over e raised to cos x.